And so what I was saying is that 1 in 20,000 would return back from here. And that is what was interesting to him. That why was there a particle that was returning over here? And now let us see a visualization. Let us assume that there is a nucleus, a good old nucleus. This is the nucleus of gold. Let us write gold simply. And so now this has a positive charge which I would represent by plus of plus. And so now what would happen is that if I am bombarding an alpha particle, here is an alpha particle that is He2 positive. If I am bombarding it down from here, then it will go, and as the positive charges repelled, it would go in that direction. And to correct me, it would not go in this direction but something like this. And if there's a particle here, then it would go something like this. As there would be a strong repulsion over here, it would just move out of the way. Over here also the same, and this particle exactly over here would come over here, would stop at a particular distance, and then again move back. This is what he assumed the things to be. Now let us just colorify the diagram. And that just makes the diagram look good. Nothing else. Yes. So the other thing that he observed, that only 1 in 20,000 was returning. That meant that around the nucleus, the electron density was less. It wasn't a crowded structure. So what I mean to say is that here is a small nucleus, and then here should be our first electron, and then somewhere here should be our second electron. Somewhat like that, I mean to say. Let me represent these electrons. This is the nucleus. So there is a vacant space in an particular atom. And now from this, he derived a formula of distance of closest approach. That is and what is the distance of closest approach? Now this alpha particle, let us represent it by a different color. This is an alpha particle, and here is our nucleus, and so over here this distance d, for which the alpha particle can come the closest. Now what I mean by that is that over here this alpha particle is deflected, this alpha particle is deflected, this is also deflected, so it can't come the closest. So the closest alpha particle would be this one, which is exactly over there. So for that we can simply do is we'll just write the forces over here. It is moving with an energy, with a velocity v, and there is a force of repulsion between them. So what we can do is we can conserve energy, and we can write half mass of electron v square equals to k q1 q2 upon the distance between them is d square. Now writing further, mev square equals to k. Charge on alpha particle would be 2e, and on the gold at nuclear it would be z e upon d square. Again writing it in a simplified fashion, it would be k 2z e square by d square. And now taking d on the left side, d square, oh sorry, there's no square, and so d would be 2k z e square upon half me v square. So this is the, okay, again I made the mistake. This is the distance that an alpha particle can closest come to. Let's go to the next formula, the impact parameter. Now what is an impact parameter? It is distance between actual line of motion of alpha particle and straight line passing through center of nucleus and parallel to the line of motion of alpha particle. So now there's a ready formula and it is represented by B, which is k z e square upon half me v square and multiplied by cot theta by 2. So now you might be wondering, what is the theta here, as we saw no theta in our any of our derivation till now. So theta here is angle between initial velocity of alpha particle and final velocity vector, and this is also called as the scattering angle. And another formula for number of alpha particles scattered at angle theta, and the formula is n is equal to, this is the biggest formula I've seen, qnt z square e to the power 4 upon 8 pi epsilon naught the whole square r square sine to the power 4 theta by 2 e square. Yes, this is the biggest formula, and let me highlight it. Like, there have not been any direct questions on this formula, or because the formula is too big to remember and nobody can actually remember this big formula as there is no derivation for it. It is an experimentally proven formula. So the only relation they ask is n is inversely proportional to sine to the power 4 theta by 2, and n is proportional to 1 by v to the power 4. V is the velocity. Okay, and that's it. We have completed with the Rutherford's model. We'll meet in the next episode and we'll learn about Neil Bohr's atomic model. That was a wonderful and gorgeous model, and you need to watch that lesson tutorial quickly as soon as possible as it is uploaded. Let's meet you in the next episode. Till then, thank you.